Today, we are going to explore some of the most important statistical tests that researchers use in their research. Think of this as your quick guide to choosing the right tool for the right data. This is the list of 16 common statistical tests which are commonly used by scientists. We will discuss all of these statistical tests one by one. First of all, descriptive statistics. When it is used to summarize the fundamental features of your dataset. It's ideal for the initial data exploration. It provides us the simple numerical and graphical summaries. This includes measures of central tendency like mean, median, and mode, and variability, standard deviation, range and variance. Next, z-test. It is best for the situation with large sample size, which is typically greater than 30, and when the population variance is known. It compares a sample mean to a known population mean to determine if there are statistically significant differences. It assumes a normal distribution. For example, testing if the average customer spending in your new online store significantly differs from the known national average for online retail spendings. Next, t-test, student test. It is ideal for smaller sample size when our samples are lower than 30 or when the population variance is unknown, making it more flexible than the z-test. It compares the means of two independent groups to determine if they are significantly different from each other. It's a robust test for many real-world scenarios. For example, to compare the average heights of girls versus boys in a specific age group within a school to see if there is a noticeable difference, we will use t-test. Pair t-test. It is designed for situation where you have two related samples or repeated measurements on the same subjects. It assesses the differences whether the mean difference between paired observation is significantly different from zero. It controls for individual variability. For example, to compare the weights of infants directly before and after a feed to measure milk intake accurately, we will use pair t-test. Welch t-test. It addresses the unequal variances. It's a crucial alternative to student t-test when you have unequal variances between your two groups or when sample size are significantly different. This is an adaptation of the t-test that does not assume equal population variances. It adjusts the degrees of freedom to provide a more accurate p-value under these conditions. For example, comparing test score between two different teaching methods where one class is much larger than the other or their score distributions look very different, we will use Welch t-test. Chi-square test, it analyzes the categorical data primarily used for analyzing the categorical data like counts and frequencies and determine if there is a significant association between two such variables. It assesses whether observed frequencies differ significantly from expected frequencies under the assumption of no association between the categories. For example, to assess whether acceptance into medical school is related to the applicant's country of birth using admission data from different regions, we will use chi-square t-test. Fisher's exact test. This test directly calculates the exact probability of observing the given data under the null hypothesis of no association between the classification. It does not rely on the approximation. This test is used for small sample sizes, especially with 2 by 2 contingency tables, the tables with 2 rows and the 2 columns. It's precise when chi-squared might be inaccurate. So We can say Fisher exact test is used when chi-square test is not giving us exact values. For example, analyzing if a new drug is effective in a small clinical trial where the number of patients experiencing side effects is very low, making traditional tests less reliable, we will use Fisher's exact t-test. Next, Mann U test. It is a non-parametric test which is suitable when your data does not meet the assumptions for parametric test, like the t-test, especially for ordinal data or skewed distribution. It compares two independent groups to determine if their distributions are significantly different. It tests if one sample tends to have larger values than the other. For example, for customer satisfaction, comparing customer satisfaction scores between two distinct product lines to see if one performed better, we will use Mann U test. Anova, comparing the multiple group means. It is a basic test in statistical test. It's used and essential for comparing the means of three or more groups simultaneously, avoiding the inflated type 1 error rate of multiple tests. It analyzes the variance within and between multiple groups to determine if at least one group mean is significantly different from the others. For example, to determine if plasma glucose level differs significantly at 1, 2, or 3 hours after a meal in diabetes study, allowing for a single comprehensive test, we will use Anova test. Next our test is the Kruskal Wallis test. It's powerful non-parametric alternative to one-way ANOVA. It's ideal when your data does not meet the assumptions of normality or equal variances. This test compares three or more independent groups to determine if their population medians are significantly different. Next, Pearson's correlation. This test is ideal for measuring the strength and direction of linear association between two continuous variables. This test yields a correlation coefficient between -1 and +1, indicating the strength and direction of linear relationship. For example, to assess if plasma concentration is linearly related to plasma triglyceride concentration in diabetic patient, we will use Pearson's correlation. Next, Spearman's rank correlation. It is also a non-parametric alternative to Pearson's, suitable for ordinal data or when the relationship between continuous variable is monotonic but not necessarily linear. It measures the strength and direction of monotonic relationship between two rank variables. Next, simple linear regression. It is used when you want to model the linear relationship between dependent variable and one independent variable and use that relationship for prediction. This statistical method fits a straight line through your data, allowing you to estimate the value of dependent variable based on the independent variables. For example, to understand how peak expiratory flow rate varies with age, this could help to predict lung function in different age groups. Next, multiple regression. It is used for predicting a single continuous dependent variable using two or more independent variables. It extends simple linear regression to accounts for combined influence of multiple predictors on an outcomes. For example, determining how age, body fat percentage, and dietary sodium intake collectively influence blood pressure in cardiovascular study. There is a little bit difference between simple linear regression and multiple regression. Logistic regression, it is powerful statistical method used when the dependent variable is binary or dichotomous, like yes, no, presence, absence, success, failure. Unlike linear regression, it models the probability of an event occurring. It is used when the outcome variable has only two possible categories. It uses a logistic function to estimate the probability that a given observation belongs to a particular category. It determines the odds of an event based on the independent variables. For example, yes, no outcome based on independent variables such as cholesterol levels, BMI, smoking status, and family history. We will use logistic regression to analyze these parameters. So, at the end of our lecture, we can conclusively say that the right test gives you robust, reliable results and helps you turn your data into real, meaningful insights. In the next videos, I will teach you each test separately one by one so you can learn them in detail. And don't forget to subscribe, share, and comment on this channel so you don't miss the upcoming lessons.